In the previous section, we saw that if a field is a gradient field, then there's a nice way to calculate a line integral by finding a potential function. So that is, if this vector field f is a gradient field, which means that the gradient of some function little f is the vector field big F, then I can evaluate this line integral simply by taking little f of the end point minus f of the starting point. Okay. So I can only do that, however, if in fact this vector field f is a gradient field, and that's equivalent to it being path independent. So then the question becomes, how do I know if in fact there is a potential function? If there isn't one, then I'd be wasting my time trying to find one. So here's a first way to think about this question of whether or not a vector field is path independent. If a vector field is path independent, so I'm assuming here that it's path independent, then we saw in the previous section that the circulation of that vector field is 0, and that's true for all closed paths C. It turns out, though it's a little bit more work, that it's true that the converse is also true. So that is, if I can show that the circulation of a vector field is 0 for all, and it's important that it's all closed paths, then the vector field f is path independent. So the implication goes both ways. So the upshot, which is more important, is that if you can find a single one closed path such that the circulation is not 0, then you know that that the vector field is path dependent, and you don't need to spend time trying to look for a potential function because there isn't one. So this is useful if you have vector fields like the swirling vector field, because you know just by looking at it that you can find a path, a closed path that goes around. Oh, that's a bad color. Let's try blue. Goes around in this direction, and the circulation around this closed path is not going to be 0, and so the vector field, so what was this vector field? This was the vector field minus yi plus xj, that swirling vector field. It's path dependent, and hence won't have a potential function, so don't try to find one. Here's a second way, a more algebraic way, to answer the question of whether or not a vector field is path independent or path dependent. And this depends on remembering that if I take the mixed second partial derivatives, it doesn't matter whether I differentiate first with respect to y and then with respect to x, or the other way around. Those mixed partials are always easy. Okay, so let's think about what happens. So if a vector field is a gradient field, then there's some potential function little f, which means that the gradient of little f is equal to the vector field. That is, if I take the partials of little f with respect to x and y and turn them into a vector field, that should be equal to the vector field f. And so here I've written f in terms of its I and j components. Okay. Now if, so still this is a big if big F is a vector field, then this has to be true, and if I take this partial derivative and differentiate with respect to y, it better be equal to this partial derivative if I differentiate a second time with respect to x. So I've written that here, down here. If f is a vector field that's a gradient field, then it must be true that these two mixed partials are equal. So the partial of f with respect to x, notice that corresponded to the I component of the vector field f. And similarly, the partial of little f with respect to y, that corresponded to the j component of the vector field f. So I would need the partial with respect to y of f1, big F1, to be equal to the partial of big F2 with respect to x. Okay, so if this is a vector field, then this must be true. So where this can often be useful is actually in the negative. So if this is not equal, then f is not a gradient field, and so it doesn't have a potential function. So that's actually where it's most useful, if I can show that these two things are not true. So here's a first example. We're going to try to determine whether or not this vector field yi minus xj is a gradient field. And we're going to do that by asking, is the partial of f1 with respect to y equal to the partial of f2 with respect to x? Okay, so it's pretty easy to calculate. F1 is simply y, and if I take the derivative of f1 with respect to y, I get 1. F2, that's the component of the j component, so that's minus x. So f2 is minus x, and if I take the derivative of that with respect to x, I get minus 1. Okay, so the partial of f1 with respect to y is not equal to the partial of f2 with respect to x, so f is not a gradient field. Okay. And since it's not a gradient field, it doesn't have a potential function, so I won't bother to try to look for one. Here's a second example. The question's exactly the same. If I'm given a vector field, is it a gradient field? And if it is, can we find a potential function? So big F1 is 2xy cubed plus y, and big F2 is 3x squared y squared plus x. Those are the I and j components respectively of the vector field. So if I differentiate F1 with respect to y, I get 6xy squared plus 1. And if I differentiate the j component F2 with respect to x, I get 6xy squared plus 1. So notice those two things are equal. Okay, so that means that f is in fact a gradient field. And now my job is to try to find a potential function. Okay, so what I'm trying to do is I'm trying to find a little f such that the gradient of little f is equal to the vector field f. So first, notice that the partial of f with respect to x needs to be equal to this I component. So I'm going to set this partial of f with little f with respect to x to be equal to 2xy cubed plus y. And then I'm going to try to integrate, and I'm going to integrate with respect to y. So if I integrate this expression with respect to y, with respect to x, of course, x, right? I'm differentiating with respect to x, so I want to integrate with respect to x. Okay, if I integrate with respect to x, I get x squared y cubed. An antiderivative of y with respect to x is xy. And then here's the slightly tricky part. There could be some constant piece in terms of a function of y. So it could have just y's in it, but no x's. Okay, so that's the first step. So this is my candidate for little f so far. X squared y cubed plus xy plus some bit that might have some y's in it. Okay, so this is, if you like, a candidate for little f. Now if I take the derivative with respect to y of this candidate, so I'm going to take this and I'm going to plug it in here and take the derivative, I'll get 3, derivative with respect to y, 3x squared y squared plus x plus the derivative of this part that had just y's in it with respect to y. Okay, now that has to match this piece, the j component of f. So I need this to be equal to, can I make that equal to 3x squared y squared plus x? And I'm just going to add a plus 0. You'll see why in just a second. So notice that everything matches up. 3x squared y squared, 3x squared y squared, x, and x. This piece came from differentiating my candidate for little f. This piece came from the vector field f. Okay, so everything matches up, and then I just need to match up the derivative of the constant bit just with y's to 0. So if c prime of y is 0, that means that the constant from which it came is just some constant k. Okay, so I'm going to try and squeeze the final answer in up here. So finally, little f, the potential function, is equal to, well, it's this. Okay, and I've determined that in fact c of y doesn't have any y's, but it could be some constant. So little f, the potential function, is x squared y cubed plus xy plus some arbitrary constant. There's the potential function.